Welcome back to our course on algorithms and data structure. We're continuing along as we're making some good progress on our material here. And so we have talked about BAG implementation. We talked about stacks. Now we're talking about queues. And so this section that we're going to be talking about now is queue, DEC, and priority queue implementation. So the implementation of the ADT queue that are in this chapter are techniques that, like the ones we use to implement the ADT bag and the ADT stack, we use either a chain of linked nodes or an array to store the queue's entries. Although the stack implementation we saw in chapter 6 were quite simple, the implementation of a queue are a bit more involved. So we also present a linked implementation of the double-ended queue or DEC, since the DEC allows allows access to both its front and its back, as ordinary chains of linked nodes is insufficient. For example, deleting the last node in a chain is not possible without a reference to the preceding node. Thus, we use a new kind of chain, one that links its node in both directions. That is, a node in the chain references both the next node and the one that precedes it. Such a chain provides an efficient implementation of the DEC. Finally, we suggest some implementations of the ADT priority queue. We note, however, that a more efficient implementation will be possible when we encounter the ADT heap in chapters 24 and 27, and that's going to come later. So here's just a reminder in the textbook of how things are ordered and roughly how things will be ordered in this lecture. So we'll talk about a linked implementation of a queue. We'll talk about an array-based implementation of a queue with a couple different possibilities there. We'll then talk about a circular linked implementation of a queue. We'll introduce the Java class library, the class abstract queue. And then we'll talk about a doubly linked implementation of a DEC, and finally possible implementations of a priority queue. So let's begin with the linked implementation of a queue. If we use a chain of linked nodes to implement a queue, the two ends of the queue will be at opposite ends of the chain. If we have only a head reference to the chain, accessing the chain's last node will require a traversal of the entire chain, making the access inefficient. Adding a tail reference, an external reference to the last node in the chain, is one approach to the problem, as the one we will take here. With both head and tail references, which node should be the front of the queue and which should be the back, we must be able to remove the entry at the front of the queue. If it is at the beginning of the chain, we will be able to remove it easily. If it is at the end of the chain, removing it will require a reference to the preceding node. To get such a reference, we must traverse the chain. Thus, we reject this option and make the chain's first node contain the queue's front entry. Placing the front of the queue at the beginning of the chain obviously forces the back of the queue to the chain's end. Since we add entries only to the back of the queue, and since we have a tail reference for the chain, this arrangement will work well. So as we're seeing in the figure, we see an illustration of a chain of linked nodes with both head and tail references. The chain contains one node for each entry in the queue. Nodes are allocated only when needed for a new entry and are deallocated when an entry is removed. So here is an outline of the class. The linked implementation of the queue has two data fields. So the field first node references the chain's first node, which contains the queue's front end, and last node references the chain's last node, which contains the entry at the back of the queue. Since both of these fields are null when the queue is empty, the default constructor sets them to null. And so we're seeing an outline of this class here. The class contains the private class node, like the one we saw in chapter 3 of listing 3.4. We also use this class in chapter 6 for the implementation of the ADT stack. So let's talk about adding to the back. To add an entry to the back of the queue, we allocate a new node and add it to the end of the chain. If the queue, and therefore the chain, is empty, we make both data fields, first node and last node, reference the new node, as we're seeing in this figure. Otherwise, both the last node in the chain and the data field, last node, must reference a new node, as we'll be showing in the next figure here, as you're seeing that now. So here we're now seeing the rest of the process of adding a new node to the end of a non-empty chain that has a tail reference. So we can see a couple of methods here. And so here is the definition of NQ as it appears. And we see the definition here and it has a performance of big O1. So retrieving the front entry, we get the entry at the front of the queue by accessing the data portion of the first node in the chain. Like NQ, get front is big O notation 1 is a big O notation 1 operation. For removing the front entry, the method DQ retrieves the entry at the front of the queue and then removes the chain's first node by making first node reference a second node in the chain, as we're showing in the figure. If the chain has only one node, DQ would make the chain empty by setting both first node and last node to null. And we'll see that shortly in the next figure. So like NQ, DQ requires no search and is independent of the other entries in the queue. Thus its performance is big O1. And so here is the illustration. If the chain has only one node, and DQ would make the chain empty by setting both first node and last node to null. Here we see the rest of the class. We see the public methods is empty and clear, and their implementation is straightforward, as we just spoke about. So let's talk about an array-based implementation of queue. If we use an array queue to contain the entries in a queue, we could let queue be the queue's front, as shown in the figure here in A. Here, front index and back index are the indices of the entries at the queue's front and back, respectively. But what happens when we remove the front entry? If we insist that a new front entry be in Q0, we would need to shift each array entry by one position towards the beginning of the array. This arrangement would make the operation DQ inefficient. Instead, we can leave another array. We can leave other array entries in the current positions when we remove the queue's front entry. For example, if we begin with the entry shown in the figure and execute DQ twice, the array will be as shown in B. Moving array entries is attractive, but after several additions and removals, the array can look like the one pictured in figure, the C portion of this. And so here we're seeing that. So let me just continue on here. The queue entries have migrated to the end of the array. The last available array entry is allocated to the last entry added to the queue. We could expand the array, but the queue has only 3 entries. Since most of the array is unoccupied, why not use this space for future additions? In fact, this is just what we will do next. And so here we're starting to see that played out with the introduction of a circular array. And so once the queue reaches the end of the array, as in figure C, you see in the top, we can begin subsequent entries to the queue at the beginning of the array. Figure 8.7 on the bottom shows the array with 2 such additions to the queue. We make the array behave as though it were circular so that its first elements follow its last elements, as figure 8.7 illustrates. To do this, we use modulo arithmetic on the indices. Specifically, when we add an entry to the queue, we increment back index modulo the size of the array. For example, if Q is the name of the array, we increment back index with that approach. So there are some complications. Using a circular array complicates the implementation somewhat. For example, how can we detect when the array is full? By adding several entries to the queue. Pictured in 8.7, we can get the full queue in figure 8A. So it appears that the queue is full when the front index is back index +1. So now remove some entries from the queue. Figure 8.8b shows the array after DQ executes twice. Note that the front index advances to 49. If we continue to remove items from the queue, front index will wrap around to 0 and beyond. Figure 8.8c shows the array after 3 more items are removed. As we remove more items from the queue, front index advances. Figure 8.8d shows the array after all but 1 item is removed from the queue. Now let's remove that 1 item. In figure 8.8e, we will see that the last removal has caused front index to advance to that it is 1 more than back index. Although the queue is empty, front index is back index +1. That is exactly the same condition we encountered in figure 8.8a when the queue was full. So here is the method for retrieving the front entry. So for information there. And so now let's talk about a circular array with 1 unused element. Not using 1 array element allows us to distinguish between an empty queue and a full queue by examining only front index and back index. In Java, each array element contains only a reference, so we waste little memory by having an unused element. Here we will leave unused the array element that follows the back of the queue. We do have a project that's listed as one of the exercises at the end of the chapter that considers a different element for those that might want to look at that. Figure 8.9 illustrates a 7-element circular array that represents a queue of at most 6 entries. As we add and remove entries, you should observe the effect on the indices front index and back index. Part A of the figure shows the array initially when the queue is empty. Note that the front index is 0 and back index contains the index of the array's last entry. Adding an entry to the queue increments the initial value of back index, so it becomes 0, as shown in part B. Part C illustrates the queue after 5 or more additions, making it full. Now remove the front entry and add a new entry to the back, as part D and E shows. The queue is full again. Repeating this pair of operations leads to the queue showing in part F and G. Now repeatedly remove the entries at the front until the queue is empty. Part H shows the queue after the first of these DQ operations. Part I shows it after all but 1 entry is removed, and part J shows the empty queue. So just kind of circling through the rest of these items here, and then the last couple of ones as well. So to summarize, the queue is full in parts C, E, and G of the figure. In each of these examples, the index of the unused element is 1 more than the back index and 1 less than front index. If we treat this array as circular, that is, front index is 2 more than the back index, thus the queue is, we can have a good idea when the queue is full. So let's talk about removing the front entry. The method DQ, like get front, retrieves the entry at the front of the queue, but then it removes it. To remove the front entry of the queue shown in figure 810A, we could simply increment front index as figure 810B illustrates. This step would suffice because the other method would behave correctly. For example, get front would return from the item that Q6 references. However, the object that previously was the front of the queue and is returned to the client would still be referenced by the array. The fact is of no real concern if our implementation is correct. To be safe, DQ can set Q front index to null before incrementing front index. Figure 810C illustrates a queue in this case. So here we have a couple of methods in terms of the implementation in DQ. So we have the front entry. So the method get front either returns the array entry at front index or throws an exception if the queue is empty. And the method DQ like get front retrieves the entry if the front entry, if at the front of the queue, but then it removes it. So so anyway, we're seeing here couple of these things and just giving you a little bit larger perspectives of some of the implementation details for DQ. So let's talk about the private method and ensure capacity. As we saw back in chapter 2, segment 235, when we increment the size of an array, we must copy as entries into the newly allocated space. We need to be careful though, because here the array is circular. We must copy entries in the order in which they appear in the queue. For example, the 7-element array in figure 8.9G is full and appears again in figures 8.11. Call this array old queue. After allocating a new array queue of 14 elements, we copy the front of the queue from old queue front index to Q0. We continue copying elements from the old array to the new array, proceeding to the end of the old array and wrapping around to its beginning as the figure shows. In addition, we must set front index and back index to reflect the reorganized array. So we're seeing the definition of ensure capacity here. And so the ensure capacity detects when an array is full by using the criteria given in earlier in segment 8.10. And so this is just a listing that you can read at your leisure. So for the rest of the class, the public method is empty, has the implementation that's shown here. So you can keep that in mind. And let's talk about the circular linked implementation of a queue. So figure 8.1 and segment 8.1 shows a chain of linked nodes that implemented the ADT queue. This chain has two external references, one to the first node and one to the last node in the chain. Recall that these references are particularly useful for a queue implementation since a queue's operation affects both of its ends. Like the chains you have seen before, the last node in this chain contains null. Such chains are sometimes called linear link chains, regardless of whether they have a tail reference in addition to a head reference. In a circular link chain, the last node references the first node, so no node contains null in its next field. Despite the fact that each node references the next node, a circular linked chain has a beginning and an end. We could have an external reference to the chain's first node, but then a traversal of the chain would be necessary to locate the last node. Having both a reference to the first node and a reference to the last node is usually more than is necessary. Since the chain's last node reference its first node, we can have a solitary reference to the last node and still locate the first node quickly. And so here in the figure, we're illustrating such a case. So let's talk about a two-part circular link chain. When a link chain, whether it is linear or circular, represents a queue, it has one node for each entry in the queue. When we add an entry to the queue, we allocate a new node for the chain. When we remove an entry from the queue, a node is deallocated. In the circular array implementation, the queue uses a subset of the fixed number of array elements available. When we add an entry to the queue, we use the next unoccupied element in the array. When we remove an entry from the queue, we make its array element available for the queue's later use. Since the addition and removals are at the ends of a queue, the queue occupies contiguous elements in the circular array. The available elements also are contiguous, again, because the array is circular. Thus, the circular array has two parts. One part contains the queue, and the other part is available for the queue. So suppose that we had two parts in a circular link chain. The linked nodes that form the queue are followed by linked nodes that are available for use in the queue. So here in the figure, we're seeing that illustrated. Here, queue node references the node assigned to the front of the queue. Free node references the first available node that follows the end of the queue. And you could think of this configuration as two chains, one for the queue and one for the available nodes that are joined at the ends to form a circle. So detecting an empty queue or an absence of an available node is easier if one node in the circular link chain is unused. The situation is analogous to a circular array that we used in segment 810. Figure 814a shows the queue when it is empty. Both queue node and free node reference the same unused node. Notice that the node reference itself. We can tell that the queue is empty because queue node equals free node. To add an entry to this empty queue, we allocate a new node and link it to the circular chain. Figure 814b shows the resulting chain for a queue of one entry. To simplify the figure, we have not illustrated the actual object in the queue. Although a node in the chain references an object in the queue, we will sometimes say that the node is in the queue. While queue node references the node assigned to the queue, free node will still references the unused node. After three more additions to the queue, three more nodes are allocated and linked into the chain. Segment 821 will describe exactly how to accomplish this. The chain is now shown in figure 814c. Again, free node references the unused node. Since queue node references the node at the front of the queue, retrieving the front entry is easy. Now, if we remove the entry at the front of the queue, we advance queue node, so the chain as pictured in figure 814d. The node that was at the front of the queue is not deallocated. A subsequent addition, since it is at the back of the queue, uses the node that free node references. We then advance free node. Figure 814e shows a chain at this point. Notice that we did not allocate a new node for the additional entry in this case. How can we tell whether we must allocate a new node when we add to the queue? We must do so if the queue node equals free node dot get next node, as figure 814 as shown in figure 814e. That was not the case when we added an entry to the queue in figure 814d. A node was available without allocating a new one, but notice in figure 814a, the queue node also equals free node dot get next node when the queue is empty. This makes sense because to add to an empty queue, we need to allocate a new node. Okay. A lot of information there. Here we have the listing for an outline of the two-part circular link implementation of the ADT queue. So you can keep that in mind. And so let's now talk about adding to the back. And so for a two-part circular link chain. Before adding an entry to the queue, we see whether a node is available in the chain. If one is not, we must allocate a new one and link it to the chain. We insert a new node into the chain after the node that the free node references, as we are about to do in figure 815a. We do not insert it before the node because we would need a reference to the previous node to do so. Getting such a reference would take time. The node that free node references joins the queue and will contain the new entry. The new node becomes the unused node, and we make free node reference it as shown in figure 815b. If a node is available in the chain, we use the node that free node references for the new entry. As figure 816 shows a chain before and after two existing nodes become part of the queue. After each addition, free node references the node that follows the back of the queue. In figure 816b, the node is available for another addition, but in figure 816c, it is not available. So here, the method in queue is easier to write and to understand if we hide the details of seeing whether to allocate a new node within the private method is new node needed. It returns false if the chain has no nodes available for use in the queue. The implementation of is new node needed is not difficult and appears later in segment 824. And so the following operation of enqueue is big O notation 1 operation. So here is the method for retrieving the front. If the queue is not empty, a queue node references its front node. And so therefore the method get front is straightforward. For removing the front, the method dequeue returns the entry at the front of the queue. If then it moves the node at the front of from the queue's part of the chain to the available part simply by advancing queue node. Part C and D of figure 814 shows a change before and after this step. Since the node that contains the removed entry is not deallocated, it still references the removed entry. Thus, we set the node's data portion to null. Like get front, dequeue is big O notation 1 operation. And here are the rest of the classes. The method is empty and is new node needed. Follow the discussion in segment 819. So here we'll briefly mention the Java class library, the class abstract queue. The standard package Java utility in the Java class library contains the abstract class abstract queue. The class implements the interface Java util queue and does not allow null entries in the queue. Recall from segment 713 of the previous chapter, the methods that were talked about in terms of the interface. Abstract queue provides implementations of the methods add, remove, and element that invoke offer, pull, and peek respectively. You can define a class of queues by using inheritance to extend abstract queue. Class must override at least the following methods: offer, pull, peek, and size. Note that the class Java util.priorityQueue, which we mentioned in the previous chapter, extends abstract queue and thereby implements the methods declared in the interface Java util queue. So to learn more about the abstract queue, consult the online documentation for the Java class library. Okay, let's talk about a doubly linked implementation of DEC. So earlier in segment 8.1, we planned the linked implementation of the queue, and notice that the front of the queue should not be at the tail of the chain of linked nodes. If it were, we would have to traverse the chain to get a reference to the preceding nodes so that we could remove the queue's front entry. Although placing the front of the queue at the head of the chain resolves our problem, such is not the case for DEC. We must be able to remove both the front and the back of a DEC. So even if the DEC's front is at the head of the chain, the DEC back will be at the chain's tail, and thereby lies the problem. Each node is a chain reference, only the next node. Thus, a chain with its head reference permits us to begin at the first node and move ahead, but from node to node. Having a tail reference lets us access the last node in the chain, but not the next to the last node. That is, we cannot move backwards from a node. And this is just what we need to do to remove the back of a DEC. What we need is a node that can reference the previous node as well as the next node in a chain. We call a chain of such nodes a doubly linked chain. We sometimes will call an ordinary chain a singly linked chain with a distinction when a distinction is necessary. So here in the figure, it illustrates a doubly linked chain with its head and tail references. While an interior node references both the next node and the previous node, the first and last nodes each contain one null reference. Thus, when traversing the chain from the first node to the last, we will encounter null when we reach the last node. Likewise, when traversing the chain from the last node to the first, we will encounter null when we reach the first node. So here is an outline of the class. The doubly linked implementation of the DEC begins much like the linked implementation of the queue given in segment 8.2. The class has two data fields, first node and last node, that the default constructor sets to null. And we can see this in the listing here. So how would we go about adding an entry? And so the implementation of the method add to back is like the implementation of a NQ given in segment 8.3. Both methods add a node to the end of a chain so that the chain's current last node references the new node. Here we also make the new node reference to current last node by passing the dex data field last node to the node's constructor. The addition to the back of a chain that is not empty is illustrated in figure 18 as we're showing, and so that's for reference. Aside from its name, the method differs from NQ only in the statement that allocates a new node. Note that the constructor for DL node has a parameter previous node, node data, and next node in that order. The implementation of add to front has an analogous implementation. When adding a node to the beginning of a doubly linked chain, we must make the chain's current first node reference the new node by passing the dex data first node to the node constructor. So here in the figure, we're illustrating the addition of a new node to the front of a chain that is not empty. You can compare the definition for add to front with the one just given for add to back. So as given here, both add to front and add to back are big O1 operations. And you can see some of those details of how it's implemented. Aside from its name, the methods differ from DQ only in the addition of the else clause. In figure 820, it illustrates the effect of the remove front for a deck of at least 2 entries. So here we can talk about remove front. And so the method remove front has an implementation much like that of DQ given in segment 8.5. But it must perform one other step. After detaching the first node, if the DQ is not empty, remove front must set the field previous in the new first node to null. This step occurs in the else clause as we're seeing in the listing. Okay, the method remove back has an analogous definition, and it's also a big O1 operation. And then finally, we'll just have a brief discussion of possible implementations of the priority queue. We can use an array, a link chain, or a vector to implement the ADT priority queue. In each of these cases, we would maintain these entries in sorted order by their priorities. With an array, the entry with the highest priority should occur at the end of the array. So removing it would leave the other entries in their present places. And figure 821A illustrates this implementation. Okay, that's going to end our lecture. So thank you very much.